Open up Lab 7.2 from the cloud. My intent here is to give you a brief tour. The first three problems that you will do are slope field problems along with IVPs as you choose. 26 is an Euler's method. 27 is an application problem, as is number 28. 27 is an electrical current problem, and number 28 is Newton's law of cooling. Get as far as you can. I will begin with, when you type in a derivative, you may use y prime. When you do so, notice that as soon as you press enter, Maple then reinterprets it to not just be y, but y of x. That does matter when you're typing in the differential equations. You would like it to be listed as a y of x. In fact, you may get an error if you do not type it as that. We're going to use commands. Through much of this year we have not used commands, but we prefer it here. You must make use of the DE tools command. So differential equations tools package, we're going to do a DE plot. Notice the syntax here. You paste in or edit the differential equation. You tell it what variable it is. The unknown here, of course, is the function y of x. You give it the window you wish for x. You choose your window for y. In general, these beginning problems are not very large. You're going to choose windows -2 to 2 or -3 to 3. If you get an error message for too large of values, you'll just modify it, make it smaller. The initial values here are in a list. Notice that the ordered pairs are in square brackets found on the keyboard, separated by commas. And then that list is inside of a square bracket as well. If you choose not to have any IVPs graphed, you just want the slope field, you would just leave this out, as well as line color. The line color command lets you dictate the colors for each of them in order. If you wish to go get a list of colors, you can click on a color and go to the help menu and look at the color options, color choices. So once you press enter on this, you will get this graph, and if the question has additional comments that you're to give text, please do so. If I demonstrate a second copy, a second version, I would copy this and paste it, and then go ahead and just edit the derivative. Again, you could type in something such as y cubed minus 4y, but it's better to have it listed as a y of x. So if I edit this to y cubed and this to be 4 times y, and in fact we'd want y of x. If we wish to keep the same IVPs, we could press enter and we would get a graph. You can tell that the values in the middle here seem to be heading towards 0. It does look like 0 itself is an equilibrium solution, possibly 2 or -2. So we may want that graph to be taller. If we go -5 to 5, we see that it does look like 2 is also an equilibrium solution and possibly -2. We might want to confirm that if we put in the IVPs 0, 2, and 0, -2. We see the green and the blue do look like equilibrium solutions. You could even add an additional one if you're wondering what's going on in between here. For example, at -0.5, square bracket, 0, -0.5, square bracket. And we need to give it an additional color. We could go with cyan. And we see that values between -2 and 2 seem to be drawn towards 0. As soon as you're above 2, it's going to climb to infinity. Below -2, climbs to -infinity. And again, we might want to experiment with that. If we would put in 0, 3, you'll probably see a warning. Sure enough, Once it gets to 3, it's taking off toward infinity so fast, it's essentially identifying there's an issue. It's not able to plot any further. So again, just fix any error like that by putting in a different value. In the end, it certainly wouldn't mean that the graph is wrong. So for the first 3 homework problems, you are typing in and graphing the slope field. Feel free to just copy and paste this command and edit it to get the graphs you would like. The next one is an Euler's method, and we're going to show a few different ways to get to compute the y values using Euler's method. It is built in a tutor, so let me go to that. You can go to Tools, Tutors, Numerical Analysis, and I prefer the initial value problem over the Euler's. If you click on the initial value problem and Maplet opens, you can type in the equation right here. Recognize that it's setting it up to be a differential equation, y of t with respect to t. Go ahead and type in the equation using t. This is your initial value. This is how far you wish to calculate out. Notice that it asks for the number of steps. It doesn't actually ask for the size of the step. So you may have to calculate that in your head in advance. When you do enter that equation, let's do one, for example, the y squared minus x squared. So we'll type y of t, and we want that squared, minus the x squared, or t squared rather. And let's click on display, and we see the graph dropping off, much like the classroom example that we had done. If you wish, you can increase the number of steps. We could go to 8 steps, click on display, it gives us the graph. Notice that it's not really giving us the ordered pairs. If you want to paste in the final computed location at the right endpoint, you could copy, highlight that, Control-C to copy it, close, it'll paste it in. You can then paste next to it, actually below it, the mathematics. Next to it I was on text. Again, it doesn't give you a list, which is maybe not preferred then. Another option is to go to the Tutors Numerical Analysis Euler. What's different about this one is when you click on step, it'll give you one step at a time. So when you click on step, it gives you the first value. Click on step, it gives you the second, and so on. Notice the comparison to a high quality solution compared to Euler's. It is a bit inaccurate. Again, when you close it, pastes it in. Since we do not get ordered pairs, it might be preferred to find a way to go get a list of values, and again, a command might be appropriate that will get us a table of values. You do need to press enter on this line. With student numerical analysis, the colon suppresses the output. If we switch it to a semicolon, you would see all the possible commands you could ask it to do. By putting in a colon, it suppresses that output. It thinks the commands and allows them. So now when we give the Euler command, it knows what we want. In this case, we are making use of y squared minus t squared at the value 1, 1, step of 0.25. Of course, that means we're going to need 4 steps. The syntax, after this is typed in text right here, but after you've pressed enter on this line, then you can type Euler on a math line, your differential equation, give the IVP, give the t equals 2, which essentially is the y value we're hoping to end up with at the very end, and then the num steps command is how many pieces you want to break that into. Again, you'll have to calculate that in advance on your own. When you put the word information, the output is this table of values. And if you wanted more steps, It's easy enough to edit that. You can switch it to 8, press enter, and it gives you the output. If you wanted to in fact increase the digits at the very end, you could put the digits command, just say digits equals 6, for example, and you'll get greater accuracy of actually a greater display of digits. If you wanted a larger set of data, you have to force Maple to do the larger set of data. So if you asked for 10 steps, 20 steps, it may not print it out, it may not give that display. Essentially, it's like it refuses to display that many pieces of data. So you use this command, interface r table size. And in fact, the first time you type it, it may resist and say 10. So you press it again and say, no, I want 40. And then when you ask for the table, it should give you the full printout. Notice the 40 is your 2 by 2 array. So it's in fact not 2 by 2, it's 4 by 10 in this case, and therefore 40 pieces of data. So by giving it this command, then it will actually give you the output. Otherwise, it'll give you a message that it doesn't want to display that many. So that's how you can get data for the Euler's method. There are two problems at the end that I wish to give you some hints on. Number 27 is the electrical circuit problem. I have it typed in for you here. Of course, you're going to input the R, which is 5 ohms, a constant, and this is voltage. And once you type that in, you can then right-click and solve for the derivative. So it's telling it to isolate for the dq dt. The function q is what we're looking for here in graphing. The other hint that I wish to provide is that in number 20, and then of course in number 27, go back and finish any of the rest of the question. But that should be enough that now once you have the derivative, you can go graph that and answer the questions they're posing. In number 28, you're told that it's Newton's law of cooling, and you have a coffee mug that is cooling. They give you the fact that it's cooling at a certain rate. The cooling rate would be proportional, so K, times the difference in the temperatures here, where Y is the temperature at time T, and R is the room temperature. Of course, that would represent then the change in temperature, the Y prime. If you want it to be with respect to time, if you type Y prime, of course, it's going to respond with respect to X. You need it to be in terms of time. Just type it in using the expression template and click on the Leibniz notation for dy dt and go ahead and enter it. The hint that I'll provide is that it's cooling at 1 degree at the moment that it's 70 degrees. So that means it's -1 since it's cooling. And of course the room temperature given is 20. So we put that in parentheses. We can solve for K. We now know the constant, which means we can set up the differential equation and then finish the problem graphically and answer their questions. Continue with the lab. Stop, pause, come back and replay as needed, and get as far as you can, and then make sure to save it and then upload it to the cloud when you're finished.